I label the points x1 and y1, x2 and y2, just to make sure I apply my formula correctly and do everything in the same order. I put the y's on top, the x's on the bottom. Subtract the y's, subtract the x's, and divide the results. It doesn't matter which points get labeled x1, y1, you still get the same answer as long as you use the same order for subtracting the x's and y's. Now here's a new question. Let's say you have those same 2 points. We just used them to find the slope. Can you use them to find the equation they belong to as well? Let's take a look. We choose any other point on the line and call it xy. Now, consider our line. It's a straight line, so the slope is the same for all parts of the line. Hold that thought. We have already applied our slope formula once to find the slope between 2, 5, and 4 minus 7. It was -6. We apply the formula again between 2, 5, and xy. Because we know the slope is the same anywhere on our line, we know y minus 5 over x minus 2 must equal the slope we just calculated, -6. And just like that, we have our equation. When we write a generic version of this equation, it's called the point-slope formula. Note that in this formula, only one x and y have a subscript because those terms identify a point on the line. The other x and y are the variables in our equation. We don't know what point they identify. We can take that equation we just found and manipulate it just like any other equation. And when we're through simplifying, what do we have? Our familiar equation solved for y, the equation we use to read the slope, -6, and the y-intercept, 17. Have you noticed that our 3 formulas are different ways of looking at the same information? This gives us several different tools to solve problems concerning equations, lines, and slopes. Great, but which one is the best? Once you have listed the parts you have and the parts you need, you can pick the tools to get you there. Here's one to think about right now. Do it any way that works. Pause the program, and when you have your answer, the equation, and the y-intercept, click play again, and we will compare solutions. I can find the slope easily from the coordinates by subtraction, so I'll do that first. It's tempting to write the x's first, but I remind myself it's y on top and x on the bottom for slope. It's also easy to overlook some of the negative signs. But I handle them carefully and come up with a slope of -8 over 5. Then I shift to the point-slope formula to find the equation and the y-intercept. Again, here's the idea behind it. The 2 slopes in the same straight line have to be equal. So we write down the point-slope formula, fill it in with our point coordinates from the point, -1 and 5, and the value for m, -8 over 5, and then simplify the equation by multiplying both sides by x plus 1, and then by 5. The 5y on the left must be simplified to a single y to get the y-intercept. So, by dividing both sides by 5, we get our answer. The slope is -8 over 5, and the y-intercept is 17/5. We've seen a number of different ways to handle problems like this. No one way is the best. You just have to decide what you're after, and then choose a tool, a formula, that will do the job. Your textbook has examples of different kinds of straight-line problems, all worked out so you can see alternative ways of handling them. After that, Try some of the sample problems in your book. The sooner the better, so you won't forget what's involved. Looking ahead, we're going to use straight line graphs in other modules to solve several equations at once. One of the last things we do will be to look at equations where the lines are not straight, more like a real ski slope.